Now we're going to talk about the lift coefficient briefly. Obviously, lift is a very complicated topic, as we've discussed before. We encountered lift first when dealing with the Bernoulli equation, but a lot of times lift is measured experimentally, just like the drag coefficient is. And you see the definition of the lift coefficient here. C sub L is the symbol it's usually given, and its definition is the lift force, F sub L, divided by 1/2 rho u infinity squared A. That's the same as the drag coefficient, except instead of the drag force, we have the lift force. So they're very, very similar in the way you treat them. One providing lift, one providing drag. They're both very important in the aeronautic industry. In the area for the lift coefficient is the planform area. So this is the area when you view it from the top, because of course wings a lot very, very thin. The area facing the flow is often very, very small. So usually the lift coefficient is defined in terms of the planform area. In terms of looking at airfoils, usually the definition of that planform area, or the way it's calculated, is based on a different C times L. So this C is the chord length of the airfoil. So chord length is the term usually used for an airfoil. This is the length of the wing, so that's no problem. That's how we would use it as well. So I'll draw a little picture of that. If you had a wing, might shaped like kind of like an airfoil like this, and then you have some length of it, nice long wing here. So that's your length going, sticking out from the airplane fuselage. And then your C would be this distance, not the surface, but the distance just from tip to tip measured in a straight line. So that little C would be just right there. Or to draw this bigger so you can see it a little better, it's not, the C is not this, it's not this line on top, it's not this line on top, it's a straight line, right through the, say, the middle of the thing here. That would be your C from tip to tip, from edge to edge. That would be your little c. So a lot of times you'll see that the lift coefficient is defined as that lift force divided by 1/2 rho u infinity squared times little c times L. So that would be the same exact thing. That's just saying explicitly that this planform area is the width of the wing times the length of the wing to give us that planform area of the wing. Now, another thing that lift depends strongly on, or CL depends strongly on, is the angle of attack. So we'll write that down, angle of attack. And so that's CL depends strongly on that. Its symbol is usually alpha. So CL depends strongly on alpha, this angle of attack. So what is that? Well, if you were to draw this, we talked about this a little bit in the last lecture, I believe. If you draw this wing, you might want to get a little more lift, so you might angle it upwards. So you're going to angle that wing slightly upwards to generate some more lift, and that's going to be your angle alpha if this is your flow coming in at some u infinity relative to, parallel to this bottom line. Your angle of attack is your upward angle relative to that incoming flow. And the lift coefficient depends very strongly on that. I think that should be obvious to you. If I tilt this wing up more, I'm going to get more lift. But we also know if I tilt that wing up more, I'm also eventually going to get flow separation. So that's going to be the thing we have to be concerned with. If you were to plot this lift versus that angle of attack for what's called a standard airfoil, and oddly, I'm going to do this in degrees so that we all have a little better sense of what angle we're talking about here. So we're going to map it at 4, 8, 12, and 16 degrees. So these are degrees of angle of attack, 4, 8, 12, and 16. And then my lift coefficient goes from 0.2, 0.4681, 1.2, 1.4, 1.6, 1.82. So it goes up to about 1.7 at its maximum, which is up here somewhere. And then it goes down to about 0.2, a little just below 0.2 for zero angle of attack, and it loops up like this, and then it drops pretty precipitously like that. So, sorry, this should be a little straighter. So you get, and this point, so it increases. This is 1, this is 2, doesn't really get to 2. CL max up here is equal to 1.72. So that's not very well drawn, but it should be right in here. So we have our lift coefficient increasing with angle of attack. As the angle gets steeper, the lift goes up and up and up. But at some point right here, we have stall, which we drew in the last lecture. So at stall, we get flow separation. So our wing is now tilted up about 12 degrees, and suddenly, we get this flow separation off the back. So the streamlines are no longer staying on the wing, and we get a recirculation zone in here, which increases the drag and starts to decrease the lift. So that's not good. So that's what, usually when you're flying, you want to avoid that situation. So this is the stall point, and after stall, as we increase even more, of course, the lift continues to go down. And that's not surprising. At some point, of course, you don't really have a wing. You just have something facing straight up and down. It's not going to fly at all. It's just going to fall. So that's not surprising there. So that's the, it turns out that the drag coefficient for airfoils also, of course, depends strongly on alpha. So CD also depends on this. CD, drag coefficient, also depends on alpha, obviously. Again, you can see that if the wing is facing like this, it's going to have some crazy drag. And if the wing is facing a better direction, it should have very little drag. That's called, it's definitely a streamlined body. You can have very little drag. But it's also true that CD increases a lot if it gets above Mach 0.5. So CD increases a lot for U infinity greater than 0.75 Mach number. And it turns out that it goes higher and higher very rapidly as the Mach number gets up close to Mach 1. It maxes at Mach 1. So CD increases until m equals 1, and then decreases again. So that's interesting. So we see the drag increasing, flying in that region of near the speed of sound turns out to be very difficult because the drag increases a lot. So planes generally avoid that speed, avoid U infinity of less than, 0.5 Mach, 0.75 Mach, less than U infinity, less than apparently 1.5 Mach. So apparently if you look at the operating conditions for planes, they often try to avoid being in this region very long. They try to get through the 0.75 to 1.5 Mach region quickly because there's a lot of drag in that region that it results from being near the speed of sound. But that's all compressible fluid mechanics. So if you really want to study about why that's happening or what's going on there, you need to get into compressible fluid mechanics, and that's beyond the scope of this introductory class. So the fundamental takeaways here are your lift coefficient depends importantly on alpha. As your alpha increases, your lift goes up. But if you tilt too much, you get stall, you get flow separation on the backside of your wing, and your drag coefficient goes way up, and your lift starts to go down. So that's something you don't want. In fact, that can be catastrophically bad for planes if they're in the right situation or the wrong situation.